Um, Welcome everyone to the One World Combinatorics on Words seminar. Our speaker today is Robbert Fokkink from the Delft University of Technology, and he's going to give us a few words on games.
Yeah, well, thank you very much, Nora. So thank you very much for the invitation. Thanks especially to Manon. She's been asking me the whole time, and the whole time I kept saying no, but eventually, I had to say yes. So I'm very happy to talk about words and about games. And what I'm going to be talking about today is actually something that was motivated by a work of Eric Duchesne and Michel Rigaud. I will be talking about combinatorial games and their connection to words. And the work that I did on it, or actually I should say we did on it, is actually quite old. We did it 3 years ago. I think Manon was defending her PhD in Liège, and then I talked about the same game that I'm going to be talking about today. But yeah, 3 years gives you time to extend and expand. So I'm going to say something about the connection between combinatorial games and words in general. It's work that I did with Dan Rost and Cisco Ortego. I didn't see Dan in the audience. He usually joins, but maybe he joined much later.
Just joined.
Okay, yeah. You're almost always here. And Cisco, of course, is not here because he's busy making money and becoming an internet billionaire in Manila. So the work that we did, as already mentioned, was motivated by a question by Eric Duchesne and Michel Rigaud, and maybe that's a suggestion for a future speaker in the Combinatorics of Words seminar. You could maybe ask Eric Duchesne to speak one day, because he's really the specialist on this topic. If you want to hear more about games, you should invite him. The results that I'm going to be talking about today are very close to a paper that came out 3 years ago by Michel Dekking. I don't know if Michel is in the audience. He's usually there too, I think. Jeff is of course here, and Neil Sloan. They wrote a paper called Queens in Exile. It came out 3 years ago in the Electronic Journal of Combinatorics, very close to what we did. So the motivating question that we had is on losing positions in impartial games. And I guess I have to explain to you what those are. So what is a game? What is a losing position? When is a game impartial? I have to explain that first. So what is a game? So for almost all of us, a game is our first encounter with mathematics. So we play games before we even learn the multiplication tables. I think everybody has played tic-tac-toe, and I'm sure most of you have also played dots and boxes, which is a slightly more complicated game. As you grow older, you play more complicated games. And one of the wonderful things about games is that everybody loves games. So most people hate math, but almost everybody loves games. And people are not aware in general that games are in fact a form of mathematics. So how do you define a game? There are different ways to do it, but for the purpose of this talk, it's a two-player game. 2 players take turns, and in a game you have positions and you have moves, and positions and moves are very much like vertices and edges in a graph. So you're on a graph, and 1 player at a time gets to choose the next vertex to move to. And the graph is made up in such a way, or the game is made up in such a way that no matter how you play, the game is always over in a finite number of moves. And most commonly, this is called normal play. The last player to make a move wins. The most common form of those games, impartial games, are takeaway games, where you have a big pile or you have piles of stones and you keep taking away stones until at one point you're out of stones and then you lose the game. If you look at the games on the slides, then you'll notice that tic-tac-toe is not entirely an impartial game. It is partial. You have a player putting the crosses and you have a player putting the bolts. So the moves are not the same for both players, depend on who has the move. So that game is not impartial. Dots and boxes is impartial, but you don't win by making the last move. You win by getting the largest number of boxes. So these are versions of games that are beyond the scope of today's talk. They are too complicated. Impartial games are even simpler than that. So we are talking about simple games, but you may get the impression that things are very simple, and they are not. There's actually a beautiful theorem. I see in the chat, but okay. I should also keep an eye on the chat, I think, if somebody has a question. I'm not always the first to respond, but I don't see any questions yet, so I can continue. Here's one of my favorite theorems. It's Hendricks-Lenstra's, well, I'd like to call it the Wimbledon theorem. A game is a set. Now, Lenstra does not call this theorem a theorem. He calls it a definition. And a game is a set that's an absolute equality. So a game is a set and a set is a game. That's actually a very deep statement. Sets are notoriously difficult to define. It took Zermelo and Frankel several years to work it fully out, and the set of axioms is beyond me. I never did well in my introductory course in set theory, but games and sets are completely equivalent. Hendrik Lenstra is an algebraist, and algebraists, I think, are the most precise people in the world. But I think he made this a concise statement because it's so very nice to declare something like this. And he warns the reader that a few words of explanation may be in order. So I'll get to that. What are the explanatory words? But before getting to that, let me show you why games and sets are actually equivalent. There's a paradox in set theory that everybody knows, I guess. It's Russell's paradox. It has to do with sets that are elements of sets. And if you allow that, then your whole theory is in disarray. Well, sets are the same as games, so you can make the same paradox for games because, well, they're equivalent. And the paradox is as follows. It's due to Raymond Smullyan, and it has to do with playing games and what is a game. So if you come to my house, you have to play a game because I'm not socially very adept. So I cannot maintain a conversation for too long. So if you come to my house, then you have to play a game. So we can get through the evening. And since you're the guest, you can choose what game we play. You choose the game and I go first. Having a choice of games in my house that's, you could say, a game itself. So you can ask, if you come to my house and you get to choose a game, that's actually a move in a game. Is this a game? And if so, then we can call it hypergame. It's a game that selects another game. So if you come to my house, you could say that hypergame is a game. And you could say, well, let's play hypergame. And then I could say, let's play hypergame. And you could say, let's play hypergame. So can you declare hypergame to be a game, yes or no? You run into the same problems as Russell's paradox, which illustrates why games and sets are two sides of the same coin. So how can a set be a game? A set is static and a game is dynamic. To understand that, you have to go back to the definition of sets. They are defined from the ground up. So in the beginning, you have the empty set that has no elements at all. And then you have the set that contains the empty set. That is a set that has one element. So that's the next set. And then you have the set that consists of the empty set and the set that contains the empty set. So you can build sets from the way up. Oh, maybe you hear in the background that there is maintenance going on in the building. A year ago, Michel Dekking was giving a talk from his house, and sometimes interrupted by some background noise we have now in the university. So let's make this a Dutch tradition. They are doing some maintenance work here, and I hope that's not audible. So anyway, sets are constructed from the ground up, and sets themselves are elements of sets. So if you want to play a game on a set, then whenever it's your move, you have to select an element from the set. And an element from a set is a set itself, if you define sets from the ground up. So you keep playing until in the end, you run into the empty set, you have no moves anymore. And then if you have no moves, you lose. So it's a bit like playing Russian dolls, opening up one doll at a time. But instead of Russian dolls, it's not a single mother, it's a whole family that you get when you open up the set. So that's the idea behind Lensstra's theorem. So sets are games and games are sets. So it's not surprising that the first theorem ever in game theory was found by a set theorist. This is Cermolo's theorem. In an address to the World Congress of Mathematics in 1912, he showed that an impartial game is either won or lost for the first player. Now, Cermolo was apparently a very active chess player, or he didn't talk about impartial games, but he talked about the game of chess, in which you have a win or a loss or a draw. And what he proved that is if both players are perfect, so the first player plays the best move available for her, and the second player also plays the optimal move in the position available to him, then everything is predetermined in game theory. The outcome is already fixed. It's almost like a theological issue you run into. If you have perfect players, the outcome of the game is fixed, and if it's an impartial game, it's either won or lost for the first player. Now, going back to Lensstra's wonderful theorem, you can ask, are the natural numbers, are they won or are they lost for player one? And how about the integers? And that's actually a trick question, because you could ask, is there a difference between the natural numbers and the integers, because they have the same number of elements. So yeah, I won't say much about that. If you're really interested in, for instance, how to play optimally, if you get the game on the complex numbers, you should consult Hendrik Lensa's 1978 paper on NIM multiplication, where he has a sequence of moves, very interestingly, on the complex numbers. So Sermelo has proved it. A game is either won or lost for the first player. And then the next question is, how do we determine that? So if you're Alice and you have to move first and you want to be a perfect player and the game is won, what are you up against? What do you have to do? Well, in your first move, you have to come up with the best move or one of the best moves. And when is a move optimal? Well, it doesn't matter what your opponent does. It doesn't matter what Bob does. You have a perfect reply. And again, no matter what Bob does, and I'm Bob, Alice has a perfect reply. So if you write that out logically, then there exists a first move for Alice, so that no matter what first move Bob takes, again, there exists a perfect move for Alice, etc., etc. So if you look at the quantifiers, then the exists quantifiers are for Alice and the for all quantifiers are for Bob. And in the end, Alice wins. Of course, it's very difficult to find these moves, but this is the problem that you want to solve if you want to win a game. And if it's won for Bob, of course, then the statement is not true. So the statement Alice wins, winning position, is almost like a true statement. If it's winning for Bob, then the opposite is true, and then you have to put a not in front of this whole array of quantifiers, and then you get the for alls are for Alice, and the exists, they are for Bob. And the problem that you have is computational. How on earth are you going to find that? That can be quite difficult. And in fact, this is equivalent to the satisfiability problem that I'm sure some of you in the audience are very familiar with. So you run into a complexity issue here. The satisfiability problem for Boolean expressions is from a higher viewpoint equivalent to deciding if a game is won or lost for Alice. So I have to say a little bit about complexity theory, which is difficult if you have a simple mind, but deciding if a Boolean expression is true or not is called the satisfiability problem, which is known to be NP complete because of the Cook-Levin problem. That's actually equivalent to winning an impartial game. And so you could think of every Boolean expression satisfiability problem as a game. So you're Alice, you get to choose your X, and then Bob gets to choose a Y, and deciding whether the expression is true or not is the same as solving an impartial game. Now, yeah, deciding whether an expression is true or not may not be the best game to have people play in the playground before they go to school. You can ask this for other impartial games or other combinatorial games, and you can ask, how difficult is it to find the optimal moves for dots and boxes, for instance? And I thought I should mention this because I'm speaking in a seminar in Canada, and this is very much a Canadian question, as it turns out, because this is a problem that Eric de Man raised about 20 years ago. And when he asked that it remains an open question whether dots and boxes is in NP or actually P-space complete. Now, I have no idea what that means because I'm simple-minded and this is a complexity issue, but this was raised in Canada 20 years ago, and there's some Dutch pride here because I found that 1 year ago, a group of colleagues from TU Eindhoven, so my Dutch colleagues, solved it, and they showed that dots and boxes is in the difficult complexity class of being P-space complete. So we have to respect impartial games. It can be quite difficult to solve them. On the other hand, if you look at the Bible of all impartial games or all games in general or combinatorial games, winning ways for all your mathematical plays, then you'll find that there's hardly any mentioning of complexity issues there. And in fact, Burlekamp, Conway, and Guy state that their approach is almost complementary to the complexity point of view, because they consider only simple games. So there's a statement that's directly from the book that they say that some people consider a class of problems finished when it has to be shown to be NP complete, but then they say, well, for us it starts here. So some games which are NP hard can be very interesting, and they, in fact, they mention dots and boxes as one of the examples. And the philosophy of winning ways is very much that you decompose a game into sub-games which have simple positions. That's what you want to solve, and then the entire game has to be assembled from these smaller games. And if you look at the games that they consider in winning ways, I think they are much more interesting for the combinatorics of word society. Here's one that I like very much. It's called the Game of Officers. It's played from the start. You play it from a single pile, but you can break up the pile. So as play develops, you can get more piles. And the rule is simply that you have to remove one stone at a time from a single pile, and then you can split the remaining pile in two non-empty piles, or you can keep one pile. And now the question is, if you start with a pile of 24 stones, is it one yes or no? And I think I didn't put that on the slide, but there's one complicating thing. I don't think you can take away a one stone if it's a final stone. So it's not simply a matter of counting stones. It's more complicated than that. There's more information on the game in the online encyclopedia of integer sequences. And the question is this game periodic, yes or no? So if a position is winning, they call it N in game theory for some strange reason. If it's losing, then they call it P. And if you start with one stone, you have no move because you cannot leave an empty pile, so no more moves there. If you start with two stones, then you win because you can just simply take away one stone and there's one stone left and you're stuck. So it starts out with loss, win, win, loss, etc. So there's a whole sequence. And people think it's eventually periodic, but nobody's been able to prove that. In fact, there's a bigger conjecture out there. You can play this game with taking away 2 stones or 3 stones at a time, splitting into 2 more piles. You can allow more moves depending on the number of stones that you take away. There's a whole variety of games, and these are called octal games. And the general conjecture out there is that all octal games are eventually periodic. I think this conjecture has been open for maybe 80 years now. And there are some sequences on the online encyclopedia dedicated to these octal games, so very specific octal games. Some of them have been solved, and for some of them, the conjecture is still open. Yeah, I should also say that the game of officers looks like a boring game because you only take away 1 stone at a time. Why is it called officers? And that's actually because this has to do with dividing an army so that officers get to command certain groups in the army. So the actual game is more fascinating in its definition than a takeaway game. And then there's a very clever argument in Winning Ways that reduces it to a takeaway game. So that's why Winning Ways is so very difficult to read. It's filled with all these extremely clever remarks that are totally obvious to the writers, I guess, but for the poor reader, sometimes you really have to break your brain to understand what's going on in Winning Ways. It's a wonderful and it's a mysterious book in that way. Now, the conjecture for octal games is that they are all eventually periodic, and from a combinatorics of words perspective, you could say, well, that's a bit boring. Can't you find more interesting words? So how about the Fibonacci word, for instance? Can you define an impartial game that produces that sequence? That would be more fun. So is there a game for the Fibonacci sequence? Again, I think there will be some people in the audience who know that the answer to this question is yes. It is a 2-pile game. Again, time for Dutch pride. It was first defined by a Dutch mathematician who's called Withoff. This is called Withoff's game, proposed by a Dutch mathematician, Willem Withoff. I say Withoff and not Weithoff, which would be the Dutch way to pronounce it. But the Y in Withoff is actually from a German last name. So I don't think you should pronounce this the Dutch way. You should pronounce it the German way or the American way. This is called Withoff's game, and it's a game not on a single pile, but it's a game on 2 piles. And these piles are not being split. They stay 2 piles forever until the last move. And there are many moves that are allowed. The rule of the game is you can take away any number of stones from 1 pile. Doesn't matter, any number. But if you take away from 2 piles, then it has to be the same number. And it's normal play. The last player to move wins. Now, the obvious first losing position, which I didn't list, is 0-0. If there are no more moves, you lose. The first losing position after that is 1-2. If you have a pile of a single stone and a pile of 2 stones, and every move you make will lose because your opponent will take away the remaining stones on his turn. So 1-2 is a losing position. And then you can go on and search for the next losing position. If you know all the losing positions, then you have essentially solved the game, because whenever it's your turn, you move to a losing position. And if you're not in a losing position, if you're in a losing position, so if you're not in a losing position, move to a losing position. If you're in a losing position, make a random move and hope your opponent makes a mistake. So you have solved the game if you know what the losing positions are. And I've listed the first losing positions here. After 1-2, you get 3-5. After 3-5, you get 4-7, etc., all the way to infinity. I've listed the first, I think, 9 or 10 positions in a table here. And if you look at the table, then you will see that the Fibonacci word is there. I'll come back to that in a second. There are lots of patterns in this table. I will also come up to that later. First of all the numbers are there. So you have 1, 2, 3, 4, 5, 6, all the numbers are there. They occur only once. If you look at the difference between the first row and the second row, that increases one step at a time. So the first difference is 1, the second difference is 2, the third difference is 3, etc. You can also see the Fibonacci numbers in there. So 1, 2, 3, 5, 8, 13. The Fibonacci numbers line up nicely in the table. And Withoff gave an explicit formula for the table. He proved that the nth losing position can be derived from the golden mean. You multiply the golden mean by n and you round it down. That gives you the first coordinate, and you multiply by n and add n, and then you get the second coordinate. And I should mention here that there's a symmetry in the game. It doesn't matter which pile is pile 1 or which pile is pile 2. So you can use this symmetry, and you can always reserve the second pile for the largest number. So the second pile, no matter what you do, is always the largest pile in this game. And then by listing these losing positions and giving a formula for that, now you know how to play this game optimally. So this is a simple takeaway game, and you can analyze it fully. It's been analyzed over and over again throughout history. But surprisingly, I think Duchenne and Rigaud were the first to observe, or actually put it in writing, that you can derive the losing positions in Withoff's game from the Fibonacci word. If you write down the Fibonacci word and you record the location of the nth A and the location of the nth B, then you get the nth losing position in Withoff's game. So Withoff's game, you could say, is coded by the Fibonacci word. And then anybody interested in combinatorics of words would ask immediately, okay, so that's a Fibonacci word. Can we find more words that are associated to losing positions in games? And that's actually what Eric Duchenne and Michel Rigaud studied in 2008, and they came up with a new concept, which they called morphic game. That's a takeaway game in which the nth losing position is given by the nth coordinate of a letter in a morphic word. So you can have a 3-pile game, and then you would hope for a word on 3 letters to code the 3-pile game, etc. And well, I think everybody thinking about this would first consider the Fibonacci word. So Fibonacci word settled. Can we find a game that codes that's coded by the Fibonacci word? And Duchenne and Nicole were able to come up with a remarkable game that is coded by the Fibonacci word. It's remarkable in several ways. First of all, it's remarkable, of course, that coding positions are coded. Or I should say losing positions are coded by the Fibonacci word. So the nth losing position is given by the nth A, the nth B, and the nth C in the Fibonacci word. And second of all, the rule set is remarkable. It's an intricate rule set. So it's not a game that you can play with your nephew or your grandchildren right away. So the first rule is not so hard. You can take away any number of stones from 2 piles. But if you get to taking away from the 3 piles, then you have 2 intricate rules that you have to study first. So I wrote them down, but I'm not going to repeat them. If you want to play the game, then you have to study these 2 rules. And I'm sure you have to pay attention to your move to check that it actually is confirming to the rules what you're doing here. So Michel isn't here, which is unfortunate, because now I cannot ask him how he was able to come up with this rule set. So it's simple enough to state, so it's not a long set of rules, but I have no idea how Eric and Michel found those rules. There must have been some, I think, reverse engineering from the Fibonacci word. And even then, the proof is highly non-trivial. It takes several pages before it's done. So it's not a trivial game. It's not a trivial proof. But in the end, losing positions in this game correspond to the Fibonacci word. And that's how Eric and Michel arrived at the motivating question for us, a question that we got interested in, but were in no way able to solve. Can you find a game that's coded by the, in general, Fibonacci word? So that's a question that is still out there for all of us to solve. So you can start from a word. You can also try to generalize Wiedhoff's game from 2 piles to 3 piles. And here's a very nice observation by Shichiki Akiyama, and I noticed that he was in the audience. So he came up with this game, I think, when did I hear it? In Vienna, maybe 4 years ago, 5 years ago, something like that. So the rule set for Wiedhoff's game is very concise. You can write it down in a very neat way. So if the number of stones that you take away from the pile is denoted by X for pile 1 and Y for pile 2, then the only restriction that you have is that the product of X and Y and X minus Y is equal to 0. So this is a very elegant way to summarize the rules of Wiedhoff's game in one formula. So the natural next step, if you go to 3 piles, is to look at the equivalent formula, but now for an X and a Y and a Z. Well, then the only formula that's a proper candidate is a product of X and Y and Z, and all the differences is equal to 0. And again, you can try to analyze the losing positions in this takeaway game. And some properties you can prove with a little difficulty, for instance, that every number occurs once and only once. So now you have 3 sets of numbers that divide all the natural numbers. But unfortunately, it's very hard to say something about patterns in the losing positions. There does not seem to be a word, a morphic word that describes it. There's a recent preprint by Frankel and Klein. I think they found the same game as Shijiki found a couple of years ago. They've written a preprint. It's out there on Frankel's homepage, but again, it's not clear what the pattern in the losing positions is. So morphic games and nice rule sets don't necessarily go together. So you can have nice rules, still not necessarily a morphic word, and you can have a morphic word, and then you really have to work hard to come up with the rule set that give the morphic word as the losing positions. So the combination words and games, an intricate one. Well, I should add that, and I add this because I think that's usually overlooked, that Withoff actually had more than one game in his paper, but he hid it all the way at the end of his paper. And he mentions, he just gives a formula, and he mentions that these sequences also give rise to losing positions in certain games. Withoff left the rules of those games to the reader. He writes something like, by their aid, modified NIM games with suitably chosen game rules might be constituted, but that's all he wrote. Withoff is a bit of an enigma, a bit of a recluse. I got interested in him and I tried to find out more about the person. Well, a couple of years ago, when I had to give a talk on game theory for high school teachers, so I thought, let me say something about Withoff, but Withoff is very elusive. All I could find out is that he was extremely wealthy. His family was in the sugar business, and well, in the 19th century, sugar was a highly prized commodity, and Withoff's dad actually owned the biggest sugar factory in the Netherlands. And sugar for the Netherlands in the 19th century, we are a colonial power. Sugar was one of the main sources of income for the Dutch economy. So you can imagine that the Withoff family was well off, and Withoff never had to work a day in his life. So he could spend his time doing things he loved. So he has several contributions to mathematics, but he never had a position at the university, or he never was, he never had a job. He could just live off the family fortune. And the one thing that he was interested in, that I could find out, the one thing that he lobbied very hard for was the possibility of taking an oath. So in those days, certain professions like judges or members of parliaments came along with taking an oath. And an oath you had to take on the Bible. And Withoff said, well, what if you're not religious? There should also be a possibility of taking an oath if you're not a religious man. And that's the one thing that he lobbied really hard for. And that's the one trace that he left that you can still find. Trying to pass a law that would make it possible for people to take an oath without involving the Bible. So anyway, going back to the game, Withoff was not a man of many words, and he just left this remark. And it is natural to ask, are there more games with sequences like this? I'm speaking for experts, so many of you must have noticed that these sequences that Withoff came up with are examples of what is known as Beatty sequences. So Beatty sequences can be defined as multiples of irrational numbers alpha and beta, such that the reciprocal value of alpha and beta adds up to 1. And then if you take the multiples, then you get complementary sequences. So you can go one step beyond Wythoff, and you can ask, is it possible to define takeaway games such that the losing positions are coded by Beatty sequences, just like Wythoff's game? Yeah, Michel is not here, but I already mentioned that I would be mentioning his name quite a lot. So in some sense, he is here. This is a problem that was studied by Julien Cassaigne, Eric Duchesne, and Michel Rigaud in a very deep paper in 2016. And one of their results is that you can actually produce these sequences from takeaway games, very special takeaway games that they call invariant. And invariant means, if I say it briefly, I think I say it correctly. Invariant means that if a game, if a move is allowed from a position, then it remains allowed if you grow the number of stones on both piles. So if you can take away a certain number of stones from the two piles, then that same move is also allowed for bigger piles. So in some sense, these are nice takeaway games, and you can find such games for all Beatty sequences. So that's a problem that was solved, problem in some sense that Wythoff left for us. But Wythoff left more. He even gave another expression all the way at the end of his paper of, and he says, well, looky here, I also have these complementary sequences. He didn't mention that these sequences are necessarily losing positions in two-pile games. He just left them because he found these to be nice generalizations of his original solution, because the difference between the two sequences increases nicely by a at a time, similar to the difference that we saw in the table for Wythoff's game, which went from 1 to 2 to 3 to 4, etc. You can produce sequences that increase like at whatever number you want, whatever b you want, and then increase by the same step, b plus a, b plus 2a, etc. And he just left these sequences there and said, well, you can check that again, they are complementary, and he leaves the proof to the reader. He was not a person of many words, and he just left it out there. Interestingly, these sequences were later rediscovered by Clark Kimberling, I think just not so long ago, and he called them generalized Wythoff sequences, which is nice because actually Wythoff produced his generalized Wythoff sequences. So maybe we should call them Wythoff's generalized Wythoff sequences. Anyway, Wythoff did not claim that these sequences were associated to games. It's natural to ask that, but that's a very difficult question. Some people in the audience may have recognized that these sequences are what they call inhomogeneous Beatty sequences. They were first studied by Frankel quite some time ago. And then, of course, it is natural to ask, and I think somebody in combinatorial game theory raised the question. I think Julien was in the audience, so maybe he can remind me who raised the question. I think it may have been Urban Larsen. Is there a connection between inhomogeneous Beatty sequences and losing positions in partial games? That turns out to be a very hard question. And the main result in the paper by Julien and Eric and Michel is that, yes, there is a connection. You can connect these inhomogeneous Beatty sequences to Sturmian words, but the Sturmian words have to satisfy an elaborate condition called the CAT condition or the CAT condition. It's a difficult condition, so that's a cat that I'm going to leave in the bag. But also this question was solved in the paper by Cassin, Duchesne and Rigaud in 2016. There is a connection between inhomogeneous Beatty sequences and losing positions in impartial games. So from that perspective, a lot has been done. Which finally brings me to the work that Dan and Cisco and I did. And this is related to a paper by Holliday in 1968. Holliday rediscovered Withoff's games. And I don't think this is Holliday's interpretation, but there's a nice interpretation of Withoff's game in terms of chess moves. So Ernst Zermelo would have loved it. If you place a queen on the chessboard, the standard queen can go horizontally or vertically or diagonally in any direction. But for this game, you always have to move it closer to the corner. So it's an infinite chessboard. So imagine you're on an infinite chessboard. You can place the queen anywhere on the chessboard that you like, and then you take turns. And whoever gets the queen in the corner first wins. And on every move, the only restriction is that the distance to the corner, so distance is the Manhattan distance, so count the number of rows and add it to the number of columns that you have to go up to get to the position of the queen. That distance has to go down, so you have to move it closer to the origin so that the game is over after a finite number of moves. Then what you're playing is equivalent to Withoff's game, because taking away from a single pile, that's like moving on a row or a column, and taking away from two piles simultaneously, that's like moving on a diagonal. So whoever gets the queen in the corner first wins, and that's why this game is called Corner the Lady. Now, Holliday rediscovered Withoff's games, his more general games that he left to the reader. And the interpretation is that in these games, the queen is allowed to slightly go off diagonal. So ordinary one Withoff, then the queen only can go to the squares that are marked with a black circle. And two Withoff, then the queen can also stroll slightly off diagonal and go to a square that's marked by a blue circle. And then you can imagine what three Withoff will be, so, or four Withoff. In these games, the queen can stroll off diagonal and get a wider and wider and wider scope. And then you can ask, what are the losing positions in those games? And they turn out to be connected to the sequences that Withoff produced and left to the reader. He left the rule set to the reader. These are also morphic games. As it turns out, there's a substitution on two letters that produces the word for these games. So there's a nice morphic game that was discovered by Holliday in 1968. Now, what did we do? So that's the work of Dan and Cisco and me. we found that if you allow the queen to bounce against a side, then you get something that can be coded, you get losing positions that can be coded by the Fibonacci word. And this result is equivalent to a result that Michel Dekking and Jeff Shallett and Neil Sloan found at the same time, which has to do with queens on a spiral. So there's an equivalent problem there that is related to this game that they solved, fortunately in a completely different way. So if you look at their paper and you look at ours, you see that the proofs are completely different. And the motivation questions are completely different, but it comes down to the same problem. So what do we have? We don't have a queen on a spiral, but we have a queen that can bounce against a side, and then we can again consider losing positions. We found a nice pattern in the losing positions if you have an ordinary queen. So the ordinary queen can only stay on the squares that are marked by the black circles. And there's also a nice pattern if the queen can bounce against a side and has a slightly larger diagonal to stroll on, so the queen can slightly deviate from the black diagonal, but only by one step. There's also a nice pattern there. And the result that we found is that the Fibonacci word codes losing positions for both these games. You have to remember the Fibonacci word. It has 3 letters, and there's a slight problem here. We're looking at a board game which has losing positions that have only 2 coordinates. There seems to be 1 letter too many, but fortunately we're saved, because if you look at the standard queen, and if the queen is allowed to bounce against a side, then you can retrieve the losing positions of that queen by deleting all the C's from the Fibonacci word, and then checking the coordinates of A and B. So for instance, if you delete the C from the Fibonacci word, then the second B will be at location 5, because originally it would be at location 1, 2, 3, 4, 5, 6, but we delete a C, so the second B is at location 5. And there you see it, the second B in the row is at location 5, and the second A is at location 3. So 3, 5, that's the second losing location. And in the same way, 4, 8 is the third losing position if you look at cornering the queen, if the queen is allowed to bounce against a side. Now, if the queen is allowed to go 1 step off diagonal, you can still retrieve the losing positions, but this time you have to delete the B's from the Fibonacci word. So then the first losing position will be 1, 3, because we omit all the B's, and the second losing position will be 2, because we delete all the B's, so we have the second A in location in coordinate 2, and then the second A will be, and now I have to count with my bad eyes, I have to count correctly, will be in 1, 2, 3, 4, 5, 6, 7, 8. So 2, 8 is the next losing position. So you can retrieve, that's our theorem, you can retrieve, you could say, 2 Withoff with a bouncing queen by deleting all the C's from the Fibonacci word. So we have a morphic game. We have 2 morphic games, in fact, but both coded by the Fibonacci word. with a very simple rule set. So we were in no way able to deal with the 4 Bonacci word or higher Bonacci words at all. But what we found was a simple game that is coded by the Fibonacci word. And it's equivalent to a result that's already been published 3 years ago by, as I said, Michel Dicking, Jeff Shallett, and Niels Sloan. Our paper will come out this year. It will appear in the International Journal of Game Theory, which took a long time, but I should say very fortunate. So maybe they were clairvoyant, because this game, which has to do with cornering a queen, comes out in a year that is very significant from a queen's kind of perspective. And it allowed us to write a short note as an addition to our paper. And that note we just put on the archive a couple of months ago. We called it Corner the Empress, and it has to do with all kinds of queens that can bounce against sides that may or may not be morphic. And we called our note, we called it Corner the Empress, and we dedicated it to Queen Elizabeth, the last Queen of Canada, or maybe I should say late Queen of Canada. I never understand the difference between late and last. That's an intricate English language matter. I think maybe it's also a personal matter, because I'm always late. So at my funeral, they'll probably say that the late Robbert Fokkink was known for always being late. Anyway, we dedicated our note in this special Queen year to the Queen of England. You can find it on the archive, and that's where Manon found it, and that's why she asked me to give a talk, I think. So in all ways, the year 2022 worked out well for queens in some sense, or maybe not at all. Now I could say something about our proof, but it's, I think, much more interesting for you to say something about what we could not prove. So we ran into a problem, and since I am talking to an audience of experts, maybe one of the experts can solve this issue for me immediately, because I suspect it has something to do with Fibonacci enumeration, but I'm not sure. So what is the problem? I took a snapshot from an article by Martin Gardner. Martin Gardner wrote something about Witthof's game in his mathematical column in the Scientific American. You can find it on the net. It's called Mathematical Games. Cornering a Queen leads unexpectedly into corners of the theory of numbers. And by numbers, he means Fibonacci numbers. Now, from that article, I copied the table, and that's the table of what Gardner calls safe pairs in Witthof's NIM, and what I called losing positions. Well, it's losing if it's your move, it's safe if it's not your move. So that's just a matter of whether you go first or second. So these numbers are the losing positions, correspond to the losing positions in Witthof's NIM or Witthof's game. And then Gardner says, note that each B is the sum of its A and its position number. That's something that is immediately obvious from Witthof's formula. But he also says, if we add an A number to its B number, then the sum is an A number that appears in the A sequence at a position that's equal to B. So you could see, for instance, I chose Fibonacci numbers, so I jumped into the middle of this table somewhere because I spotted some consecutive Fibonacci numbers there, 8 and 13. They're in position 5. This is the 5th losing position. If you add 8 to 13, you get 21. If you look at 21, it's the 13th losing position. So the B number, 13, corresponds to the losing position that you have to check if you want to find the sum of the two, 8 and 13. So 8 plus 13 gives you the 13th A number, etc. If you do that for 4 and 7, for instance, 4 plus 7 is 11, and lo and behold, the 7th losing position is equal to 11. That's a remarkable property of the table. The table has several remarkable properties. With some difficulty, you can actually prove this from Witthof's formula, but it's a property that's not immediately obvious at all. It's intriguing. And now it's natural to ask, do we find something similar if we have a queen that can bounce against the side? So I've written down the table of losing positions for the queen of, for the bouncing queen. And sometimes the formula works and sometimes it almost works. So for instance, if you add 3 and 5, then you get the number 8. But if you go to the 5th losing position, what you find is 7, not 8. Okay, one off, too bad. Let's try the next one. 4 and 8. If we add 4 and 8, we get 12. Now we look at the first number in the 8th losing position, 1, 2, 3, 4, 5, 6, 7, 8, and we get to number 12. Hey, here it works. 4 plus 8 is equal to 12. So sometimes it works and sometimes it doesn't. Now let's check 6 and 11. 6 and 11 adds up to 17. What's the 11th losing number? Oh, it's 17. It works again. Now it works again for 7 and 13, but I think for 9 and 16, you can spot from the table that it doesn't work. If you add 9 to 16, then you get 25. If you check the 16th losing number, you're in trouble because it's not out there in the table, because it doesn't fit on the slide. But you can see from the second row that 25 is in the second row. So it's not going to appear in the 16th losing position. In fact, what you will find in the 16th losing position turns out to be 24. Again, off by -1. So there's a pattern out there. For some n, this formula holds. For others, you need to subtract 1. Now that's a pattern that we could only observe. And there's probably some Fibonacci numeration behind that. So there's a question for you, experts out there in the audience. Can you please help us and settle this issue? Can you prove that the formula is correct up to a -1? And that brings me to my final slide. So thank you all for listening. Please solve the problem.
Oh, thank you so much, Robert. Does anyone have a quick question for Robert?
Hi, Robert. I'm not positive. Thanks for a great talk.
Yeah.
I'm not positive, but maybe this is in the paper with Neil Sloan where we prove some things about the inequalities of the Fibonacci numbers. And
yeah, so yeah, you'll find that the relation is off. And I don't remember correctly, but I thought that this would still hold for the very large numbers, but maybe I'm wrong. So I think Neil Sloan first thought that there would be a certain equality. And then you found a counterexample. That's what Michel Decking told me by computation. So yeah, I'm also not sure, but if it's not -1, then can you prove that it's -2?
Yeah.
Or +1 or -1 or -2?
I think if you look in our paper,
Yeah.
we have an inequality. I'm not sure it's exactly the same thing that you want, but
yeah,
that's my question. But we do have this inequality, and the reason why it comes is because of the two imaginary roots of the Fibonacci recurrence sometimes lining up in the right way to make it off by 1 or 2.
Yeah, okay,
So,
by 2. Okay.
Well, I would, yeah, check the paper. Yeah,
I'll check it again. Yeah.
Okay.
I think I looked at it and I could not immediately find why it was the same, but maybe it's exactly the same.
Okay, all right.
Does anyone have anything else?
I have a comment on the last question.
Yeah, sure, go ahead.
Can you go back to the previous slide?
Previous slide, yeah. This one?
So yeah, so 8, so 3 plus 5 is 8, and on the 5th column you see 7, so it's off by 1.
Yeah.
But 8, where is 8? 8 is on the 2nd row. On which column? On the 3rd column, so the AN column. So we have BAN, which is equal to AN plus BN in this case.
Oh, okay. So now, if you look at BAN, yeah,
maybe also equal to the sum. And then if you do it for 4 plus 8, BAN, that's on the 4th column, and it's 11, so it's off by 1.
Oh, yeah. So there's another one. Yeah.
Okay, and now 9 plus 16, the ABN was off by 1. But the 25, where is the 25? 25 is on the 9th column, so it's BAN.
Yeah.
So it's either one or the other.
Oh, yeah. So it's the same thing. So, but yeah, so I have both Jean-Paul and Jeff, telling me how to do it. I'm not surprised. Again, this may be in the paper by Jeff and the others on the queens on the spiral. It's a Fibonacci enumeration issue.
Mm-hmm.
So yeah, interesting. Interesting observation. I'd have to think about it. Yeah, I'd have to think.
That was Julien Kessen, by the way.
Oh, it's Julien. Okay. I didn't see who was talking. I was just guessing that it was Jean-Paul. So Julien, thank you very much for pointing this out.
Any other questions? All right. If not, thank you again, Robert.
Well, thanks for having me.
Oh, yeah, you're welcome.
Thank you very much, Robert.
See you next time.
Yeah, we'll see all of you next time.